We all set? Okay. Okay, so I'm going to start out by talking a little bit about the intersection between the field of robotics and the field of rehabilitation, and also where there's opportunities where I think for some more intersection. So first, if we look at rehabilitation, these are all images that I took from RIC's website. So RIC is a rehabilitation hospital in Chicago. And in particular, at RIC, we are treating impairments that might have to do with people's sensory systems, their cognitive abilities, or their motor abilities. Now, if we pause for a moment and we look over at robotics, and we see at the top here like an industrial manipulator. So this is what robots look like when they first kind of started entering the field in general in the 1960s. Now we're starting to see robots that make it into the home, like the vacuum cleaner robot is certainly the most ubiquitous. There's starting to be robotic toys. And then these are some future domains where we would like to see robots collaborating with humans very heavily as sort of teammates or as aides. And one thing that has characterized this transition from the top of these images to the bottom is autonomy. So the robots at the top, these are robots that require a very structured environment. They are not necessarily sensing their external environment, and they are not necessarily safe to operate around humans. So they are inside of cages when they are on work, the floors of a factory. Now, one of the things that we can sort of leverage within this transition is that in order to address autonomy, we have had to come up with ways to synthetically sense the world, reason about it, and also actuate within it. And we can leverage these advances to help address some of the impairments in humans that we're trying to help with rehabilitation. So what the field of rehabilitation robotics looks like from the clinical side, so this is not academia, but the clinical side, what you actually see interacting with patients are typically therapy machines. So the top left there is the Locomat. This is a lower limb gait rehabilitation system. There's also planar 2D arms that help with rehabilitation after stroke often. And then there's also these exoskeletons. So this is the Rice wrist. This is a device at UCSB. SV. And then what's missing from these set of images would be like prosthetics and orthotics. And so all of these serve a very important role, but these are not autonomous robots. So they are not sort of sensing the higher level world and making decisions in that. And they're not meant to. I'm not trying to imply that these are not filling the role that they're meant to fill. Now, if we look on sort of the other side, there's an emerging field of assistive robotics that's been around for maybe about 10 years now. And here's an example of the Robots for Humanity project, which is Charlie Kemp's group at Georgia Tech. And they're actually using a PR2. This is Henry, a patient or a collaborator of theirs, who has had a very severe, I believe, stroke. And he basically has control over his mouth and his eyes and his thumb. And that's about it. He can't talk. That's just it. Yeah, so you see here he's kind of smiling, but he can't actually speak. And so what he wanted was the PR2 to actually become his sort of body surrogate. So he wants to be able to control the robot. Here the robot is shaving him with an electric razor, not a blade, but still, that's the desire that Henry has for this. And there's a lot of people in the world who would like this as well. Up top here we see the Pero seal robot. This is a surrogate for pet therapy. So partly this is a cultural thing. You can't have pets it was developed in Japan, and you can't have pets in Japanese nursing homes. You also don't need to worry about the robot dying if you forget to feed it, things like that. So it can be practical in that sense as well. And these, within the field of assistive robots, we often do see very high levels of autonomy. These are autonomous agents interacting with the world. Now, the work of my lab kind of falls in between these two worlds. In particular, we are interested in assistive machines and in making the control of these machines easier for people who might struggle to control them. So certainly the most ubiquitous assistive machine in the world is the powered wheelchair. Prostheses, both upper limb and lower limb prostheses, are also we also see those a lot. And there's also exoskeletons that we want to use eventually for mobility. Currently, they're mainly just being used for therapy. And we're starting to see things like a robotic arm. This is the Jayco robotic arm, which is a commercially available arm that's meant to be mounted to a powered wheelchair. Now, one of the challenges in this domain is that as you go from something like the powered wheelchair, which is a two-dimensional control problem, to controlling something like a robotic arm, the dimensions that you need to control, the controllable degrees of freedom, really increases. And the standard interfaces that we use to control these devices no longer cover all those degrees of freedom. So for a powered wheelchair, that's a joystick. That's just a 2-degree of freedom system. There are 3-axis joysticks, which is what comes with the Jayco. You can see here in the inset, he's actually operating it with his foot. So a 3-axis joystick also has twist. That gives you a 3-dimensional control signal. That's only half of your control space, because an end effector to control the position and then the orientation is a 6D control problem. So what they do with the Jayco, at least in their commercial control kit, is they do what's called mode switching. So you basically push a button on top of the joystick to switch between operating the position dimensions to operating the orientation dimensions, which is feasible. But it's a little bit cumbersome, and it's not accessible to everyone. So you see he happens to be using his foot to control this device, but a lot of people, by definition, who would benefit from the aid of an assistive robotic arm don't have that level of hand dexterity. And they're limited instead to these control interfaces, like if you've ever seen a sip and puff, which is like the straw, which is like a 1 or 2D control signal, dimensional control signal, and it's non-proportional, which means if you blow harder, you don't go faster. So it's basically a switch that's being turned on and off in 1 or 2 dimensions, and we want to use this to control these high-dimensional systems. So the idea is that we can leverage robotics autonomy to help with this. So in particular, if we want to turn our assistive machine into a robot, this won't be a surprise for anyone in this room, I'm sure. We start out with an assistive machine. We add sensors that are able to sense the external environment, because this is what's going to help make the control easier if the robot has an idea of what needs to happen in the larger space of the world. We add some computing and artificial intelligence, normally most commonly in the form of path planning, at least at the moment. And then your assistive machine has turned into an assistive robot. So there are some challenges and special considerations within this domain, especially if we think about the field of sort of human-robot teams, more classical examples of that, like search and rescue teams. Excuse me. And it can be informative to look at the world of prosthesis adoption. So here is an example of what's called a body-powered prosthesis. It is a mechanical device. It doesn't have any electricity running through it, unlike the myoelectric prostheses that you see. And the way that it operates is basically, you see that he's got a strap on his shoulder, so you operate one joint at a time, and what you do is you kind of throw your shoulder in order to get it to bend and then to lock it into place. And that's how you operate this prosthesis. So it seems like, and then usually there's a hook at the end of it, which actually this style hook is actually extremely functional in replicating the majority of human grasps. But it seems like sort of a no-brainer in this domain, right? That having an arm would be better than not having an arm, and that if we could make the control of this easier and add some electric motors, that would be better. And yet, we see within the field of prosthetics a very high rate of prosthesis rejection. In particular, we see about 1/3 of body-powered or myoelectric users using the prosthesis only as a passive device. So it's just aesthetic. They are not actually using its functionality. We see a 1 in all overall rejection rate for all prostheses. Now, this partly has to do with the problem domain. 90% of activities of daily living you can do with one hand. And so if you are not a bilateral amputee, or if you don't have a bilateral amputation, you'll just adapt with your hand that you do have left. There's also, and so for that reason, that gets into this lack of functional need, that people are pretty functional with just one hand. But there's also things like discomfort, excessive weight and heat. Socket fit is a huge thing with myoelectric prostheses. And so the sort of take-home message for this is to just come up with an engineering solution isn't enough. We need to reason very critically about what the sort of needs of the patient are and what their wants are. Lots of times there's a lot of examples of really beautiful engineering solutions that don't get adopted. And so in particular, some of the challenges and special considerations in this domain is user acceptance. That's kind of number one. If your device isn't going to get used and it was intended for this kind of domain, you pretty much might as well not have built it. One is also the flow of control authority. So if this machine is going to be partly autonomous, it's going to be sometimes taking control from the human. You never want to do that when the human isn't expecting it and when they don't want you to do it. Then also they will not want to use your device. And then also these sort of interfaces for feedback and control. So I touched upon this a little bit to to begin with. And this is the sip and puff that I mentioned. The other device that's commonly used to operate powered wheelchairs is a switched-based head array. So these might be actual physical switches or proximity switches, but basically you kind of roll your head to do turning or to go forward. And it's, again, this on-off switch. It's not a proportional control interface. And so what we're interested in also is that if you're limited to these kinds of interfaces, what kind of signals can you expect from the user? Also, what can you maybe provide to the user as feedback about the system's doing? Or also, what information can they give you back about how they feel about how the machine is performing? So in my lab, we are building a smart wheelchair platform, and what we're really prioritizing in our development is customization and low cost. So in particular, every user is going to be different in their particular impairments. They're going to be different in their personal preferences. And because of this, we think that it's going to be important for them to be able to customize exactly what the autonomy looks like on the machine and how it's sharing control with them. Low cost is because we don't expect these devices to be covered, or autonomy to be covered by insurance anytime soon. So when a therapist fits someone for a powered wheelchair, they fill out a stack of papers about this thick to justify every cushion on the chair, every aspect of the chair. You have to justify it in order to get it reimbursed by insurance. And so the only way that autonomy is going to make it onto that list is if we have extensive user studies that say this is necessary for these financial reasons, things like that. And that's going to be a long way out. It is our dream that eventually this will be the case, that when you get fit for your powered wheelchair, you also get fit for the autonomy. But that's going to be a while out. So we want our system to be accessible or financeable at least by some people out of pocket. So one way to do that is to integrate with commercial hardware. So in general, or in particular, the system that we're developing assumes that you have your own powered wheelchair and your own control interface, and that this already would have been covered by insurance. There's a type of control interface called an expandable input, and it's meant to interface with all different sorts of control interfaces, which means also that the signals going to the control module aren't as proprietary and encrypted as a lot of the other wheelchair models or prior ones. Pretty much all wheelchair companies now have an expandable input model out there. So the idea is that we can interrupt that control signal, pass it through our system, reason about it, modify it, and then send it back along this pipeline, and then the control module of the wheelchair itself actually then executes the control. We have a small hope that this maybe won't void the wheelchair warranty, but that probably won't end up being the case. But it's the wheelchair's controller that's actually going to be executing it. And we want to emphasize good performance with these non-proportional control interfaces. And that can be kind of the lower bar for our system, with the idea that any richer control signal we get on top of that would only improve performance. Okay, so the way that we're handling customization is to have a modular software system. So in particular, there's all these different sorts of software modules that someone might choose to opt into or out of. And the system can kind of handle that seamlessly. Also, within each of these modules, there is a particular control sharing strategy for how these transfers of control happen between the users. So this is just a simple example of a linear control sharing strategy. But the idea is that these strategies are parameterized, and we can tune the parameterization to the user. In future work, we're going to actually have this tuning happen automatically, and hopefully also incorporating user feedback, but that's still on our to-do list. Now for customization, not only will we have modular software, but also modular hardware, and this is what will help keep costs low. So in particular, everything in the gray box is our system. So the computing power and electronics we need to have there. But then the idea is that you can have these different sensor modules, and they will unlock different software modules. So it might be that without the IMU, you can't do terribly accurate long-term path planning, but you could do sort of like visual servoing in order to do obstacle avoidance using just like an RGBD sensor, like the Kinect. So our baseline system just uses one Kinect. It works a lot better if we add in more sensors, but it works nominally to some degree if we only have that one sensor. And the idea is that then people can add on additional sensing components based on what they want the wheelchair to be able to do functionally, and also what they can afford financially. So our architecture, sort of at a high level, is that, in a nutshell, is that we have a behavior controller at a high level that's going to be choosing between multiple, it's going to be autonomously detecting goals in the environment and then choosing between them, and also based on the user's input. And then a single goal will be selected. It'll be passed to the low-level behavior controller, and here again, we're going to reason about users' input and arbitrate between the control that's being generated by our controller versus what's being offered by the human. And as I mentioned before, we are expecting that we can adapt both the autonomy behaviors and the control sharing, but that's still on the pipeline. So if we look first just at goal generation, so the first step for goal generation is goal perception. This is work, and I apologize if this video seems to be running slow. Actually, they both do. This is some work that my student Matt Derry did a couple of years ago, or like about a year and a half ago. And it is doorway perception. So what it is a geometric approach. We're just using the depth data from a single RGBD sensor, or a single Connect. And what it's doing is first looking for vertical planes in the world. So that's what you see with all the sort of magenta pink dots. It's then searching along those in a stripe that's about at the height of the wheelchair. And that's just for computational efficiency to look only along this stripe. And it's looking for gaps. It's looking for gaps that are a little bit less wide than what is the standard like ADA specification for how wide a door should be. This is the Americans with Disabilities Act. So it looks a little bit narrower than that to about 2 times that, and then anything wider than that we figure is like open enough space that we can just drive through it. If it finds a gap that big, it also searches top to bottom to see actually if we've got enough height for it to also be considered a doorway. Since we're extracting that plane, we get an orientation for the doorway, which means that once we've got this position and orientation for an identified doorway, we can actually set navigation goals for our autonomous path planner that is able to reason about things like obstacles. And so what we do is we set basically about a half a meter in and a half a meter out, so that by achieving the first navigation goal, you're all lined up to go through the door, and by achieving the second one, you actually pass through the door. Another goal perception that we've looked at is docking locations. So if you were, for example, trying to orient your wheelchair at a table in a restaurant, it was very crowded, and you were using one of these limited control interfaces, it can be challenging, or it requires dexterous maneuvering. So here's another geometric approach. This is work that my student Siddharth Jain did. And basically, we're again looking for surfaces, or planes, but now it's horizontal. We are then seeing whether or not we think this horizontal surface is rectangular, including squares, or circular. And then we have mechanisms for searching around the edge. We can either take the width of the wheelchair and kind of slide it around the edge, or we also look for circular objects on top of the surface with the idea that it's probably a plate or a bowl, and that could be a place setting. And so we use these 2 approaches to kind of anchor our candidate locations. We check for clearance underneath, and then we get a list of candidate docking locations. So once we have this set of candidate goals, we then need to arbitrate between them. And so in particular, we do that based on a confidence calculation. And this is an example of a confidence calculation. I'll go into it in a moment. If you see here with my left thumb, I'm teleoperating the wheelchair. When I first stop giving a control signal, it's pretty ambiguous which door I want to go into. And so the robot does not take over control. But when I now take off my thumb here and I've given a little bit of signal to the left door, then it goes. And so this confidence calculation is based partly on our perception confidence. So did we just see a doorway once, or did we see it many times over multiple frames? And then also whether or not we're sort of aligned with these signals, control signals that we're getting from the human. So realigned both in terms of heading, and then also how far away are we. So we're not going to take off for a door that's across the way, because they don't need our help yet anyways. We're not at the dexterous part of that maneuver, and we might be wrong about what they're trying to do. Okay, so once we've decided on a goal, we send that goal to an autonomous path planner, and then we need to, again, reason about how to share control with the human if we're still getting a control signal from them. So we have lots of different sorts of strategies for how we can interpret the human's control signals. What you saw before there was basically if I get no signal from the human, the robot should take over control if it's confident to do that. You can imagine that no control signal from the human should be interpreted as stop. You can imagine that the robot doesn't ever take over all the control. There's all different sorts of ways to interpret that. Some work that a master's student did a couple of years ago in my lab was to actually look at inferring how this control sharing should happen from demonstrations. So this was just in simulation. This was when we were just starting with this project, actually. And what he did was provide a bunch of demonstrations that basically, for each type of door configuration, where it could be completely open space on the other side, it could be like a hallway, or it could have just a right wall or just a left wall. We showed for each of these configurations 3 demonstrations at the fastest we would ever want to go through, and 3 demonstrations at the slowest we would ever want to go through. And then we encoded all this information within a Gaussian mixture model. So then you could now reason as well as distance to obstacles. So now the sort of task constraints were sort of inherently encoded within the variance of this model, so that when you saw a lot of variability, it probably meant that we weren't very task constrained, and so it's okay for the user to deviate from the path planner, but otherwise we're going to keep them closer to the path planner. Another way that we reason about command arbitration is for safety monitoring. So in particular, we're always monitoring the environment to see whether or not there's an obstacle nearby and whether or not we have an impending collision. And if we do, we will sort of gradually step control away from the user and over to the autonomous path planner. Now, we want to do this in a way where we aren't just wrenching control right away, but also we can't do a super fine calculation to just step it really small, because that'll be too computationally inefficient. So we sort of balance it. We found that a step size of 0.2 works pretty smoothly. And so here you can see that this alpha is basically when alpha is 0, all of the control is with the robot, and when it's green, all of the control is with the human. So as the human's driving up to the obstacle, control gets taken away from them, the robot takes over and diverts them around, but then control goes back to the human as soon as is safe to do so. So again here, if you watch my thumb, you'll see that I'm trying to drive directly into the chair, and here I'm even continuing to try to drive it to the right into the chair, but the robot is going around. Now it has no higher level goal in the system. It is just forward projecting my commands in order to infer what the goal is. And then I try to hit Matt, and it still goes around. So with this project, the next steps, as I mentioned, is that we want to look into adaptation, both autonomously and also getting feedback from the user about what it is that they preferred and liked. And then also user validation. So you notice that my robot doesn't have a seat, so this is a development platform so far. But one of the real nice advantages we have is that our lab's actually located in a hospital. So we have sort of unparalleled access to patients and their clinicians. And so getting their feedback on this system is going to be important, and that's something that we'll be hopefully moving into in the coming months. In terms of adaptation, I was just going to take a step back really quickly and briefly overview, and again, the video is running slow and I apologize, and just quickly take a step back and overview some of the work I did during my postdoc and my PhD. So I didn't work in the field of rehabilitation before I started as faculty 3 years ago. Instead, I was working just in the field of robot learning from demonstration, and in particular on after you had demonstrated a behavior, how do you then provide corrections to the robot? How does a human provide corrections to the robot? So during my postdoc, I was working with the robot called the iCub right here. And so here you can see that the corrections that are being provided are tactile. We've got a ring of tactile sensors around the wrist of the robot and on the back of the hand. And we're using this, it responds to a person's touch, and we use that to provide pose corrections. So here, Eric's providing a correction just at the end, but it actually could be provided at any point throughout the correction, or throughout the execution. During my PhD, I was working with the Segway RMP. This is a very different kind of robot, so it's a dynamically balancing inverted pendulum, which means that a tactile correction isn't a good idea, because if you push it, it pushes you back. You'd also have to run around next to it and try to push it, which wouldn't make sense either. So, so here we are using actually sort of to call it a graphical interface is generous. It was an octave plot, but basically a plot of the 2D ground path on the ground, of the mobile robot on the ground, with also some color coding to give us an idea of how confident our machine learning prediction was at that point of the state space. And then we can basically just select a big chunk of these points and apply a single correction over it. We called these corrections advice operators. They were mathematical computations, and basically, so you could have basically a formulation, for example, that said turn tighter, and what that would translate into is like reducing your translational speed and increasing your rotational speed, for example. But you could have these sort of corrections, apply them, and then you now get a whole new chunk of demonstration points, of corrected demonstration points. So we used these in a couple of different ways. So one is that There we go. So first is for policy refinement. So this is just that you're trying to improve the behavior that you demonstrated in the first place. So here we see the segue. This is just a toy problem for illustration purposes. But what it's doing is basically driving a sinusoid on the floor. It was given the sinusoid as sort of a piecewise trajectory. So it's got these point turns. It's pausing in the middle of the execution. But we provide it with corrections about turning tightly and going faster and things like that. And then we see that we sort of eliminate these point turns. We've got no pause in the middle. So you're able to elicit behavior that was never a part of the original demonstrations. Now at EPFL, we also looked at using corrections for policy reuse. So this is now that we actually want to bootstrap from something that was already demonstrated to learn something new. So what you saw at the beginning there, maybe I can go back. Oops. No. All right. Sorry. Sorry. Apparently. Okay, so what you're going to see in this video is that the iCup is first going to try to pick up the with the ball policy, which of course has the wrong hand orientation. Now we provide one correction, which we then apply that correction over the whole data set. So we rotate the entire data set, and so now it's been applied, and we don't have to do this sort of iterative process. Now what we can also do, since we were modeling this within a Gaussian mixture model, we can also show variability in the task constraints. So you see that we showed one demonstration at the top, one demonstration at the bottom, because you can actually grasp the can in different locations. Now if we're clever about the ordering in which we're teaching things, we're going to do another rotation, and now that variability that we had along the length of the can will be applied along the edge of the tray. Okay, and then a final way when we use it was policy scaffolding. So this is work from my thesis. This is just a simulated domain. It's just a point robot trying to drive along a racetrack. And what had been demonstrated was to go straight, turn right, or turn left. But things like straightening out after turning right was never actually shown to the robot. But what we did do is provide corrections, and in the end the robot was able to travel along the whole racetrack, and also at a faster speed than the human was actually ever able to demonstrate. So in this case, we can enable more complex behaviors than the teacher can originally provide if the teacher is able to provide corrections instead of only demonstrations. So these kind of general ideas are accessible to people who aren't robotics experts. They just need to be able to show something instead of being able to sit down and write the control policy or the computer code. Which makes them good candidates for going out to the general world. If we're thinking about sending them out with our assistive robots, where you can maybe have the person themselves or an aide or caretaker provide these demonstrations or provide these sorts of corrections. And so these kind of ideas we're going to be incorporating into our assistive robotics work, but that's still all on the horizon. Okay, so some other projects going on in my lab. So one project that I've been working on in collaboration with Todd Murphy came out of when I first arrived at Northwestern, and I was coming from this field of demonstration learning, and he was coming from the field of optimal control. And so what's really nice about optimal control is that you get all these great guarantees about stability and the performance of your controller. Whereas demonstration learning is largely a data-driven technique, so it does not derive from the same sort of mathematical theory. And so what we were trying to see is if there was any sort of in-between between these two worlds, this overlap between them that we could come up with. And what we've come up with is something that we call trust-based control. And what you can do is view the human's interaction with a controlled system as like a disturbance, and you can reason about whether or not it is taking you away from or outside of, for example, like the basin of attraction of your current controller, and things like that. And you can use that now to compute an explicit measure of trust in the human. And then you can reason about how much should the human be allowed to interact with this machine. So if this human has a history of always providing demonstrations that are going to destabilize the system, you don't incorporate their correction to its full extent. So in particular, you can provide these sort of dampen downs. You can scale down the step that you would take from the current control policy to what would be executed if you tried to execute the user or the human's demonstration or correction. And so this is stuff that we've been working on for about a year now. And we're using it on a very different platform. He has a bunch of robotic marionettes, which is a very under-actuated system, and that's the system we're using to look at this. But we're planning eventually to bring it around to the field of rehab and assistance as well. Another project that we've looked at is partial automation for prostheses. So this was funding that we had for a summer for my student Matt. And in particular, so this is a prosthetic arm that's being developed by the Center for Bionic Medicine at RIC. It's a 5-degree of freedom arm. And this is sort of the standard approach, not necessarily to controlling this arm, but to controlling prostheses in general. So in particular, you get the raw EMG signal. You do some sort of signal processing or classification on it. And then you get out one class that you say, this is what I'm controlling, and you feed that to an open loop controller. You just control one dimension at a time, one controllable degree of freedom at a time, and that's how it works. And the reason why we're limited to that is that basically, if you right now, for decoding myoelectric signals or EMG signals, we can decode reliably maybe like 10 to 12 classes. And each of those classes only encodes a half of a degree of freedom. So you've got like elbow flexion or extension and elbow flexion. And that's 2 separate classes. And so basically it means that if we can decode 10 to 12 classes, we can control 5 to 6 degrees of freedom. So this does not handle, for example, what if I want to move my wrist and my elbow at the same time. And also, when I say 10 to 12 classes, that's pretty much been recorded down here. If you're now recording only from the upper arm, the signal decoding is even smaller. Now, there are different techniques that have been being developed to address that. So in particular at RIC, there's something called targeted muscle reinnervation. That's really neat stuff. That's actually mapping the residual nerves from an amputated arm to a larger muscle, like the pectoral muscle. And then because of that, it's distributed over a larger muscle, and you can use a bigger array of EMGs, and you can actually pick up decode a much higher number of classes. But that requires surgery, which actually isn't so much an issue for someone with an amputation, because they probably are having surgeries anyways. But for the meantime, it's really just in exploratory phases. So that's sort of so that's the exception. The general rule, certainly if you see a commercial prosthesis, is that it's going to be controlled according to this kind of paradigm. And partly, the fact that it's an open loop controller, this is because upper limb prostheses don't even have any kind of position sensors in them. And that's because it's not really worth the weight. So weight is a huge issue with these kind of arms. And basically, if it's just that the user is observing it anyways and they're directly controlling the signal, there's no reason to have a closed loop controller. But the idea that we had was that so basically in this arm, they're developing it to be extremely lightweight, and they are going to have 2 Hall sensors in it. They told us if we had gone forward with the project and bought it from them, they would have given us a position sensor in each of the joints. So that kind of enables closed loop control. And the idea that we had was to have a very, very small number of automated controllers on the arm. And by small, I mean maybe 3 to 5 that you could select between, like you were selecting between different functions on the arm, and that these then, once you started them, would operate on multiple degrees of freedom at once. They could do things like repetitive motions, so like oscillatory motions would normally require you oscillating in the signal you're sending through the EMG, which would be really fatiguing. You can do oscillatory motions, you can do the simultaneous coordination of multiple degrees of freedom. And then what we use the EMG for is to actually modulate the parameterization of these controllers. And that's what makes a single controller applicable to a bunch of different scenarios, because the human is controlling that. So we just implemented this in simulation. But here you can see Matt. This is a crank turning task. It's coordinating. I think it's actually coordinating 3 degrees of freedom on the robot arm. And what he's doing with the EMG signals is first he's tuning the amplitude. So in this case, it's a rotational controller, and so what he's tuning is the amplitude and the frequency of that rotation. Once he gets it at the right amplitude, then he basically does a co-contraction to switch between which meta-controller he wants to be operating on, and he then made it go faster. Now he's controlling it in the opposite direction. It's going to slow down until it eventually goes the other direction. Now, the EMG decoding we were using for this was dead simple. We weren't using any kind of classification or anything like that. It was just the biceps and triceps. But that if we had gone forward with the project, we would have gone into much more sophisticated EMG decoding. Okay, another challenge that I kind of touched upon earlier was how do we control these higher degree of freedom systems, especially with these limited control interfaces. So this is the Miko robotic arm in my lab. It is the sibling edition of the Jaco that I was talking about earlier, or the research edition sibling of the Jaco that I was talking about earlier. It has just 2 fingers instead of 3. It's smaller, it's lighter. It also has more sensors and it's cheaper. And so it's actually a really great arm for robotics research. But the question is, if you now are limited to having only 1 or 2 dimensional control signal and it's also non-proportional, how do you control this in a way that's not entirely frustrating? And currently, commercially, this just doesn't happen. People are not using these kind of interfaces to control these kind of robotic arms out in the general public right now. So one thing that we're working on that's a collaboration with Sid Srinivasa at CMU is assistive teleoperation. And the idea here is that if the robot has a sensor and it's able to observe the external scene and observe objects in the scene that you might want to manipulate or interact with, that you can then take the signals that you're receiving from the human in this lower dimensional space as cues about which object you think they're going for, or that they want to interact with. And the more confident you get about which object, the more and more the robot takes over control. Again, the way in which it takes over control can be customized. And the idea is that by the time you get to the point where you're actually interacting with the object and performing the dexterous manipulation, you've offloaded a bunch of the control, maybe all of the control, to the robot arm. And so in those videos, now they don't start at the same time, so it's a little bit unfair, but this is basically with assistance from the robotic arm, and you can see the user's actually going for the box, and so once they give that control, that signal that disambiguates that yes, I want to go for the box and not the water ball, the robot takes over, and you can see how much longer it takes to do that. Now this was just some pilot data, but we're actively developing this project as well. And in particular, with the studies that we're going to be performing with high spinal cord injury patients at RIC, we're going to look at customizing this arbitration function, this control sharing function, and also the confidence measure. So how do we decide from the signals that we're getting from the user, how do we determine our confidence in which object the user wants to interact with? And then also the robot policy itself. Another project that I'm collaborating with with Sandro Musa-Valdi at RIC goes actually into interface design. So far I've always been talking about these sort of commercially available interfaces, low-dimensional interfaces. But one thing that Sandro's been developing in his lab is what's called the body-machine interface. Now this is a vest of IMUs that the a person wears, and what they do is they basically have someone perform kind of like what they call a body dance, where they just any residual motion they might have. People who have very high spinal cord injuries often still have a little bit of residual motion left in their shoulders. So they have them perform this sort of body calibration dance, and then they perform dimensionality reduction over that. So far they're only using PCA. And then you just take the 2 strongest components of this dimensionality reduction, and you use that to control, so far they've been controlling in 2D space. So what's nice about that interface is that it is conforming to the form factor of the user. So whatever residual motion the user has left, we can extract information from that instead of having the user needing to conform to this form factor of the device. It also encourages movement. So there's actually a possibility that we will see some rehabilitation gains with this. And his lab is currently performing a clinical trial to see the effects of that. So far they've used the body-machine interface to control in 2D space, so they've used it to control the position of a cursor on a screen, to play certain games, to type on a keyboard. They've also used it to control a powered wheelchair. What we want to do is use it to control the Miko, so 6-dimensional control problem. Now, there's something like 4 or 5 IMUs on here that are each given 9-dimensional signals. So we have the dimensionality there. There's a lot of redundancy, but it's an unknown question whether or not someone can actually generate 6 distinct control signals with their body like this. So the idea is that we want to use autonomy to help train the user. So in particular, we can have the robot able to execute the policies on its own, and we start out with the user controlling only a very low dimensional part of this. So it might be, for example, that the user is just controlling the speed of the execution, and but the actual pose of the robot is being handled by the autonomy. And then it might be that we jump up to sort of like a three-dimensional control, and it's again like position or orientation. It might be that the user is giving signals on when to transition between piecewise trajectories. So if we had like a feeding function that was first going to approaching the bowl and then scooping and then coming towards the mouth, and the user could have control over when each of them stops, because the user has a lot more perceptual awareness than our system. But the idea is that we keep iteratively taking control away from the robot and giving it back to the user. And ideally, what we want to do is use robot machine learning to actually elicit human motor learning, which we think would be a really cool thing to be able to do. So the robot can actually automatically infer, based on the user's performance, whether or not it should unlock another control dimension. And this is work, again, that we're just getting started with. Okay, and that's it. Since I have a very young lab, I always make a little bit of a pitch at the end. So the goal of my lab is that we are trying to make assistive robots that make a human more able through the introduction of selective automation. So we don't want to take over all the control. We still expect there's a human in the control loop. But we want the automation to be customizable and teachable by the user, and then also adaptable. Because not only will they have different preferences, but actually their abilities and wants will change over time. So it might be that they have more pain on a given week and they want more help that week. It might be that they are in therapy and their ability is improving. It might be that they have a degenerative disease and their ability is degrading. We've got a really great lab space in REC that we're extremely lucky to have. So we're right on the shores of Lake Michigan in downtown Chicago. And so if you're ever in Chicago, please feel free to look us up and come by and visit. And then lastly, I'd like to thank, of course, my graduate students, my PhD students, who, as you all know, do the majority of the work. And so that's Matt Derry, Alex Broad, and Siddharth Jain. Also, there's some undergraduates and alumni from the lab as well, and my funding institutions. So with that, I'm happy to take any questions.
Okay, we have a little time for questions.
So you touched on this a little bit at the end, but I was hoping to go more into it about how, what kind of feedback you want from the user, whether, for your door example, you could have a feedback where the user just selects the door from the beginning and the robot just completely navigates through the space to the door versus kind of nudging the wheelchair to get through the door.
Yeah, so there's lots of different forms that the feedback from the user can take. And it could be just instantaneous feedback on how to execute just this one time, or it could be actually changing the policies. Right now, we are making the assumption that we are only getting information through these limited control interfaces, that we're not, for example, putting a touch screen. And it's not because we don't think that's a worthwhile route to follow. It's more because of this, that we're trying to stick to this idea that we're going to introduce as few additional components onto the system, and we're going to push it as hard as we can with just software for now. Now, what I expect practically is going to happen is that, we'll get to a certain point with our system and we'll say, okay, now let's put on a touch screen and let's see how performance changes, and is this actually the right decision? But I think that there's a lot of, in terms of what a user might want to be telling us on the fly, I think the only way we're going to fully know that is through studies.
Getting back to wheelchair control,
Yeah.
Someplace along the line of development, you're going to have to make a decision whether or not you can find a control site and sensors that you'd be able to get a user-generated signal to operate the chair, or you say, we're going to just provide an automatic control. So some of the wheelchair interface options that you showed are very, very old. And there's been a bunch of new ones. So I was wondering if you did any research to try to figure out if there was some place on the person's body that you could sense and provide a good enough signal to control the wheelchair.
Yeah, that's something, so the short answer is no, we haven't actually done any of those kind of studies with patients. Now, obviously, depending on someone's impairment, especially with certain degenerative diseases, you see that people have different amounts of mobility all over their body, right? And there are these, very, very limited throw joysticks that require almost no movement, and Yeah, exactly, and things like that. And so those are all options. So we're basically, our research so far is after that point, in the sense that we assume we're getting some kind of control signal from the user. It might be low bandwidth, it might have latency, it might not be a clean signal, but that we are getting some signal. And we aren't, at least with the exception of our collaboration with Sandro, we're not looking at alternative ways to gather that signal. Now, I think that that's a really interesting place to go. The one study that I do know of is, I forget which company it was. Some prosthetics company did a huge study of all these different places around the body that you could try to use to control a prosthesis, and basically came up with the fact that nothing was better. I think they looked on the foot, they looked on the back, they looked at all these different sorts of areas, and it was inconclusive whether or not it's because people expected to use their arm muscles to control an arm, or things like that. But and that's solely EMG control. But that's the only thing I know of someone doing a study like that.
Well, let me add to that.
Okay.
So some Stanford students and I developed a ultrasonic head tilt sensing system. It's like over 30 years ago now.
Okay.
And it worked really well.
Yeah.
And so if you had a good enough control system, you can get to right where you want it to go. And your visual system will be able to make all the corrections you need.
Okay.
So we had this going for about 5 years or so. Tested it at the VA, and we were on 60 minutes for 43 seconds. So that's another place. And then I heard of somebody using basically controlling a prosthetic with their feet. That most of the time when you use a prosthetic, you're standing still, so you can use your feet. So
Yeah, I've heard of.
there's all sorts of ingenious things that
Yep.
you can try. And in my thought is to give the user as much independence as possible in controlling things.
Yeah, absolutely. And I mean, I think that's a whole other really rich research area. For the time being, we've focused on these commercial control interfaces for the reasons of cost, and also that they're really user validated, even if everyone kind of universally agrees that we can do a lot better. And so that's just that we've limited the scope of our current research, but I agree that that's a really rich research area.
Thank you.
Yeah.
Other questions? Sorry, Dan.
No worries. Hi.
Hi.
Regarding that IMU best that you had shown, where you can essentially extract the two most outstanding principal components left over from any residual movement that that patient population has.
Yeah.
I was curious, have you ever considered using maybe brain-computer interfaces or over-the-head electrode sets to maybe extract additional?
Yeah. So, so this is all Sandro's research. So it's really not my area. But I know that one of the nice things that he always cites in comparison to, for example, brain-computer interfaces, is that this interface actually requires you to move. So it possibly can have rehabilitation benefits, whereas brain-computer interfaces don't. There's also I think that for controlling a wheelchair, you can definitely, and we see examples around the world of research groups that have controlled a wheelchair with a brain-computer interface. In terms of controlling arms, it seems to be that that's probably only going to be with implantable devices. That it's just not that using just a head array or like a scalp calf, that you're not going to be able to get a rich enough or consistent enough signal to actually control these high degree of freedom systems. The jury's out there. There's actually some people who believe that you're actually just training your scalp muscles to move, and that it's not actually that you're getting the true motor signal. There's another issue that wearing those caps make you look even more impaired. So it's an undesirable interface for that. But I think implantables are a totally different story. Yeah.
Thank you.
Okay. All right. Thank you very much, Professor.
Yeah.